Right. So what I was telling you is that we started off the other day with aromatic compounds. In aromatic compounds, we learned that what is the cyclic planarity and conjugate conjugation will be, and it does follow 4n plus 2 pi electron rule. While anti-aromatic would also have cyclic planar and continuous conjugation, except that it follows only 4n pi electron rule. Non-aromatic, on the other hand, could be an open chain, it could be non-planar, it can have non-continuous conjugation. Based on that, we saw a few examples, which of them are being aromatic, anti-aromatic, and non-aromatic. Now, continuing that, suppose if this is the case, we have four-membered ring. If we have like this, or if we have this way minus, or if we have minus and minus, these are all four-membered rings. See which of them is going to be aromatic or not. First one, you can see ring conjugation is there. Pi bond can be delocalized and it is moving around the ring like this. So ring conjugation is there. It is cyclic as well, correct? And what else you need to check? Planarity. Planarity is also there. So yes. And it is following which type of rule? It is following 4n pi electron rule. 4n pi electron rule as in uh, number of electrons, you know, should be multiples of 4. So n is equal to 0, 1, 2, 3, and so on. So when you put n is equal to 1, you can see there are 4 pi electrons coming. Here also 1, 2. Total 4 pi electrons that will keep moving around. So it is following 4n, it is following 4n pi electron rule. So from here we can say that this is going to be aromatic in nature. Which is aromatic in nature. Sorry, anti-aromatic in nature. From here, if you check out, it is also planar. It is planar. It is cyclic. It also has ring current, but it is having 4n plus 2 pi electrons. So which means it is following Huckel's rule properly. Therefore, this is aromatic in nature. Check out, this pi can be moved here, and that can be moved here, that can be moved here. So only one pi bond keeps moving around the entire ring like this. Hence, this is the aromatic form. Now check out here, this pi is not able to move anywhere. It is localized. Therefore, this is non-aromatic. Here, one pi electron, one minus. So it is moving here, but it is not completing the ring because you can see this is sp3 hybridized carbon. So that will also make it non-aromatic. It is also a non-aromatic case. Last one, we have one pi here, one pi here, and one pi here. Okay, it is equivalent to writing that this pi, if at all it comes here, this minus will move here. So we will have minus. So all these minus charges will keep moving around four carbons and pi will keep moving around in the center. So which tells us that it is aromatic. Why aromatic? You see it is planar, it is cyclic, ring current is completed, and it is following 4n plus 2 pi electrons. Because you can see this is one pair of electron, this is one pair of electron, this is one pair of electron. And now totally it is making 4n plus 2 pi electron system. So this is also correct. Clear? Next, if you see 5-membered ring, in 5-membered ring, you could have cases like this: positive, negative, that's it. Suppose if you have a case like this, where we have one positive, two pi bonds, you can see it will complete the resonance here. So it is definitely planar. It is completing the cyclic. It is cyclic, planar, completing the ring, but only has 4 and pi electrons, which means it is anti-aromatic. Here you can see one, two, three pi bonds. All of them are, completing all the rules here. Cyclic also, ring current also, and it is following 4n plus 2 pi electron system. So it is aromatic. Here there is no. Here it is sp3 hybridized carbon. Here it is sp3 hybridized carbon. Here it is sp3 hybridized carbon. So all of them are non-planar in nature. Hence it is non-aromatic. Sorry. Okay, so far clear. Now what we'll see, we'll only write all the heteroatomic species. So where you have heteromolecules, like in this case we have in 5-membered ring, we will usually have boron at the center like this, 15th. It is covered by oxygen with a lone pair on it, sulfur with a lone pair on it. Then we have nitrogen covered with a lone pair on it. We can have two combinations like that. Check guys, please try whether they are aromatic or not, or what they are. If they are not aromatic, then what they are. See the first one. Here we have an empty orbital. So this pi will definitely delocalized here. So this pi will move here, positive charge will come here. And that positive charge will keep moving around. So ring current will be over. Since it is ring current possible, which means it is cyclic, ring current is possible, planarity is there, and it is following 4n pi electron rule, which means it is anti-aromatic in nature. Clear? See the next one. This pi electron will be involved here. This pi will be moving here. This pi will move here. So which makes it cyclic. Also has ring current. Also planar in nature, and it is showing 4n plus 2 pi. Sorry, 4n plus 2 pi electron rule. So which means it is aromatic in nature. This compound is known as furan. Next one. Lone pair moving here, pi electrons here, pi electrons here. So which means this lone pair, this pi, and this pi, they all three will be involved in resonance and complete the ring current. So they are cyclic, planar, Ring current is possible, and it is 4n plus 2 pi electrons present. Hence, it is aromatic in nature. Same way, lone pair on nitrogen present on here, so that will delocalize here. It will keep moving, so which makes it aromatic as well. This is this is named as thiophene. That is thiophene. 17. This is pyrrole. Pyrrole. Next, lone pair on oxygen will keep moving here. This pi bond will keep moving here. And this lone pair will also support boron because boron has an empty orbital, H and empty orbital here. Hence, count the number of pi electrons: 1, 2, 3. 3 odd number of electron, odd number of pi bonds. So definitely that makes it aromatic. So this is going to be cyclic, ring current, planarity, and 4n plus 2 pi electrons. Yes, this is also aromatic. Ninth is also aromatic. You can see that this lone pair participates here, pi bond moves here, pi bond moves here. So it is also aromatic in nature. Last one, if you see that this lone pair does not have any involvement, only the pi bonds inside are moving around and complete the resonance. So this is also aromatic. The name is pyridine. This is termed as pyridine. Any derivatives of benzene, they are all aromatic in nature. For example, if you take any group on benzene, like you have this, and any such group present on uh, benzene ring, suppose if there is OH, it is called phenol. If there is NH2, this is aniline. If there is CH3, it is toluene. If there is double bond like this, it is called styrene. If there is COOH, it is called benzoic acid. All of these are aromatic because aromatic nature comes mainly because of these three pi bonds. As long as these three pi bonds are present, whether you have withdrawing, donating, it doesn't matter. They are always going to be aromatic. Next, if you see, there's a seven-membered ring now. In seven-membered ring, we'll be studying mostly about this. Suppose if you have, cyclic forms like this. Now, check it out, how it is there. In these three cases, first one, pi bond, pi bond, pi bond. Delocalization is up to here, but this carbon is not being involved. So definitely this is non-aromatic. Here, pi bond, pi bond, pi bond. And plus charge will allow it to make conjugation. So conjugation will keep happening throughout the ring. Since this will happen throughout the ring, it is aromatic. Here also minus charge will keep moving. It will keep happening throughout the ring. But the number of pi bonds now will be 1, 2, 3, 4. Even number of pi bonds means it is anti-aromatic. You'll get this as anti-aromatic. Okay. If you see one reaction here on this basis, what you'll identify that when you have pH thrice C plus, pH thrice C plus We have like this, where we have two hydrogens, like this. Now what happens? This C plus, correct, which is present here, will take one H minus. If it takes H minus from here, it can make it pH thrice CH bond, and because H minus has lost, this compound will become aromatic, and that is what we will have like this. And positive charge will be here, and this is what, you know, the positive charge which you are getting. This is called tropylium ion, tropylium cation. And see, such type of aromatic compounds which have some positive charge or a negative charge, we call them as quasi aromatic. Quasi aromatic. Quasi aromatic, as in they would have some charge on it. I hope all of you understood this point. Right. Now, see, students, based on aromatic nature, you will be asked questions. For example, if you have, suppose we have two types of bromine. There is one bromine here, there is one bromine here, and we are treating that with AgNO3. Immediately, the reaction will happen where we will see this bromine is not disturbed, but this bromine becomes positive charge, NO3 minus plus AgBr. AgBr is a precipitate. So to form the precipitate, Ag plus will immediately take Br minus, gets a positive charge on this carbon and makes it aromatic. So the ring is becoming aromatic and it is a positively charged and it is looking like in a salt form. Such type where you have positive or negative charge, which we call it as quasi-aromatic. Quasi-aromatic compound is formed here. Same way, wherever say there is an opportunity of getting an aromatic form, they will definitely go for it. Suppose if there is chlorine here and we are treating that with SbCl5, SbCl5 will immediately grab that chlorine, convert this into positive charge like this, and this will become SbCl6 minus. So again, a salt kind of a form here. This is also aromatic in nature. So this type of questions are asked whether they are aromatic or not. Okay. Now on a similar lines, other questions which will be asked here, we suppose if you have non-anti-aromatic like this and you are treating that with Fe plus 2, sorry, Fe plus 3. If you are treating that with Fe plus 3, Fe plus 3 will oxidize this, which means it will take one electron from here, one electron from here, and converts that into positively charged species. This way it will retain back its aromaticity and 2 moles of Fe plus 2 will be formed. 2 moles. So it has undergone reduction. Same thing can be done where this non-aromatic compound is getting reduced. So if you react that with sodium, 2 moles of sodium will make it double bond here with minus charge and minus charge. The minute it gets minus charge, this is also becoming aromatic in nature. Okay. Same is the case wherever you see like that, double bond, hydrogen and hydrogen is there. So we immediately react with sodium or potassium. So potassium will leave electrons here and this will become aromatic. Get double bond minus and K plus, and releases half mole of H2 gas. Like this, we'll get with gas also, we'll get few reactions. I suppose this point is clear. Right. Now, so far, whatever we have studied is about a single ring. When you have multiple rings, in case of multiple rings, how we need to think. First, let us talk about naphthalene. Structure is like this. Naphthalene structure would be like this. Now you can see ring current wise, there is an easy way of doing it. You just count the number of pi bonds which are in resonance. One, two, three, four, five. Odd number means always aromatic. Even number means it could be anti-aromatic. So this is definitely aromatic. Clear? And it has one isomer also. It has one isomer which looks like this. And it is a 7-membered ring. 5 and 7-membered ring. So you can see this as 1, 2, 3, 4, 5, 6, 7-membered ring. And this is 5-membered ring. This is how the structure has been. So you can see this is azulene. The name is azulene. This is naphthalene. Now students, check out. For this, what we can see, in case if at all I put this pi bond here, okay, then this gets positive charge, this gets negative charge. Let me show you how it is. Suppose if you move this pi bond here and makes minus here, double bond here with positive charge here, like this. You see this side of the ring here, no? This is a aromatic ring, and this is also becoming an aromatic ring because you can see one, two, three. These three pi bonds will make it aromatic. Here also one, two, three. This makes it aromatic as well, which means this ring will always have negative charge. This ring will always have positive charge. So we can write these two rings in this particular form. This particular form where without writing these pi bonds, I'm writing the hybrid of it where this will have continuous negative charge and this structure will have continuous positive charge. So you will see a strong dipole moment is created between them. So molecule will have very strong dipole moment like this in this direction. Okay. In fact, the mu value is around 0.8 dB units. So we can say this is a dipolar molecule. It is a dipolar molecule. It exists in a blue color solid state, solid crystal form, and it is highly stable in nature. Okay. While mu here, if you see, it is unstable. So mu, I mean, mu is 0 and it is completely non-polar. That is the difference between naphthalene and azulene. Next compound is anthracene. Anthracene as in two rings instead of two, we will have three rings here like this. This is anthracene. So in anthracene, if you see, okay, we will have 14 pi electrons, 14 pi electrons, and this is aromatic in nature. Just like anthracene, we have one more ring here like this, and this ring continues here, which looks similar to anthracene. This is also aromatic in nature. This is called phenanthracene. Next, cyclooctatetraene. Cyclooctatetraene. Suppose if we talk about this one, you have octane here, cyclooctane, and if you put double bonds here, this will become cyclooctatetraene. Double bond here, double bond here. Okay. Now, actually, if you check out, it looks like an uh, anti-aromatic form because it has one, two, three, four pi bonds. Four pi bonds relevant to anti-aromatic form. But it is not anti-aromatic in nature. It is actually non-aromatic in nature. Why it is non-aromatic? Because this would always try to change its geometry and try to become non-aromatic like this. Now, if you see that we have a double bond here, double bond here, one double bond here, and one double bond here, like this. So this is the tub shape which it adopts, tub shape or a cot shape. Okay. To avoid 8 pi electron closed loop, or ring current, it becomes non-planar, tub-like shape. Hence, it is non-aromatic. So do not mistake with this. It appears like anti-aromatic, but it is always non-aromatic in nature. Clear? But if there is any chance by which it can get aromaticity, then it will compromise on that planarity. It will definitely compromise on that planarity. Like for example, if you have plus and plus, now what would happen? Now we'll have only 6 pi electrons, which means it is aromatic in nature, which means this is aromatic because it has 6 pi electron cloud. Clear? Same way, if we have minus and minus. Same thing here also, you can see it has 1, 2, 3, 4, 5. 5 means odd electron. Odd electron means aromatic. So this is also aromatic in nature. Now, sometimes instead of directly giving it as a molecule, here the double bonds will be given with regards to double bond O, like oxygen here. Now, this molecule, to keep it aromatic, that C double bond O will always exist like a single bond only. What I meant to say is that this exists mostly in this form, like this, with O minus and plus, because when you keep it this way, it would definitely become aromatic ring. So this is also aromatic in nature. This is aromatic in nature. The name is tropone. If we have benzene, for example, benzene like this, and there is one more pi bond outside. This pi bond is always localized, and that is not participating in any kind of bonding. So you need to check only aromaticity based upon the six, pi electrons present here. So that will make it aromatic in nature. That's it. Dear students, these are the cases you must be pretty aware of, how they could be acidic, basic, and so on. Okay. Now let us do a few questions here. Double bond given here with two hydrogens and pH MgBr with pH having negative charge, magnesium as plus charge. Please write the products. Do these two questions. Done, students. See the first question. pH minus strong base. It will take away this proton from here and makes it into an aromatic ring. So we'll have this as double bond with minus charge and MgBr with plus charge on it plus PHH, which means benzene. So we'll get benzene to be prepared this way. Next, same way, this is butyl lithium or lithium butyl. So Bu minus will take away H plus from here, and as it takes H plus, this will get minus charge and makes this ring aromatic. So it will become aromatic in nature. Lithium plus BuH. This is the product formation. See this compound here. Next compound. This is called calcine. Now, calcine has two rings and a pi bond in between them. If that pi bond is distributed such a way both rings are aromatic, then they will always exist in that form only. They will exist in plus and minus form. Okay, one ring will always have plus charge, one ring will always have minus charge. To make both the rings aromatic, you have to ensure that both rings are getting aromatic. Since both rings are getting aromatic, this pi bond will hardly dominate. Therefore, it is easy to rotate this bond. Hence, here we require very less, very less rotation energy barrier, which means energy required to rotate the bonds. That is very less here because that pi bond would not exist at all. Okay. The same logic can be applied for the quasi aromatic cases where we have the similar structure like this, a double bond connected with here also this pi bond. Let's see, this is how the pi bonds are. Now this pi bond won't exist here anymore. This will get positive charge, this will get negative charge, so that both rings can become aromatic in nature. Clear? Here also very less rotational barrier, and this is also aromatic. Both the rings are aromatic in nature. Suppose if you have a structure where both side the same compound is present like this. In such case, if you try to distribute these pi electrons, one would become positive charge, so it will become anti-aromatic. One would become aromatic. So if you see this case, we'll have single bond here, double bond like this with negative and positive. Although this ring may be becoming aromatic, but this ring is becoming anti-aromatic. So therefore, this type of a movement is hardly seen. Hence, there is a very high rotational energy barrier. Would have very high rotational energy barrier. Okay. Lastly, there are few examples which makes it very highly acidic because of aromatic nature. One of them is this one. Suppose if you have a square with a double bond here and double bond O, double bond O, OH and OH, like this it is given. Now the minute it loses these two electrons, so imagine it loses this 2H plus, the structure would be double bond with O minus and O minus, with double bond O here and double bond O here. Now this O minus will close here, double bond will move. So you can see this pi bond will keep moving throughout the rings. So we'll have four canonical structures. So I'm just writing the resonance hybrid, how it looks like. We'll have a hybrid where this pi bond is keep moving here inside the ring. And with respect to all oxygens here, all four oxygens, there is a movement of electrons here and movement of electrons here, movement of electrons here and movement of electrons here. And all of these are getting 2 minus charge. So 2 minus charge is moving around. This is how it looks like. So you can see there is a 2 pi electron, 2 pi electron cloud, which we also call it as aromatic. So therefore, after releasing H plus, it will achieve a highly aromatic form. After releasing H plus, it achieves highly aromatic form. This is called squaric acid. and very strongly acid in nature. Okay, next 14th, same thing. We have double bond OH here, OH here with the double bond. So imagine the same thing here also. Losing out those two H plus ions makes the entire ring aromatic. That's why it is also highly acidic. Next, infused ring, infused ring system, fused ring system, transferring of aromaticity from one ring to another ring. That is called annihilation. See, mathematically, how you need to understand. Suppose if you check benzene, benzene has a resonance energy of 152 kilojoules per mole. This much is the benzene's resonance energy. Resonance energy is always negative. I'll introduce that negative sign also. But the minute we fuse the ring, one more benzene ring with it, it will become naphthalene. Because of fused ring, this pi bond is donated here also, here also. So the effective resonance per ring will decrease. Now, there is resonance energy what we are expecting. What we are expecting is 2 times minus 152. But actual resonance energy actual will be less. That is found to be minus 252 kilojoules per mole. So due to fused ring, annihilation happens, which means resonance energy decreases. Clear? Any doubt so far? Normally, when you write Ha as a weak acid, imagine it is a weak acid, it is dissociating with H plus and A minus. Weak acid will always exist to have an equilibrium. And if there is an equilibrium, there is an equilibrium constant associated with it. Here, the equilibrium constant is called as ionization constant of acid. Ionization, ionization constant, ionization constant of acid. So it is a weak acid ionization constant will be always equal to product's concentration divided by reactant's concentration. This is the value of Ka. Ka will always be equal to product's concentration divided by reactant's concentration. Okay. Now, this you will learn in equilibrium other way. But as of now, to keep it simple, understand this H plus concentration will always be equal to product's concentration. I mean, Ka value will always be equal to product concentration by reactant concentration. So from here you can see that if the H plus concentration increases, then Ka value has to increase. Okay. So if you compare two acids, one of them has, imagine, more H plus concentration. If it has more H plus concentration, we can say it has more Ka value. Higher the Ka value, more is the acidic nature. So remember that higher Higher H plus concentration implies more dissociation or ionization of acid. Okay, and that implies acid is more acidic, and it has higher acidic strength. So we will check out on the H plus concentration. And since we can relate that if the H plus concentration is more, we can say the Ka value is more, implies more acidic nature. Now, in here, one thing we need to take care of is that uh, we can represent H plus in terms of pH, where pH is termed as minus log of H plus concentration. Suppose अगर H plus concentration 10 raised to power of minus 3 है, so we can say pH is equal to minus log of H plus concentration, which is equal to minus log of 10 raised to power of minus 3, and that makes it 3. So you can see that H plus can be converted to simple numericals to remember. So lower the pH value, higher the H plus concentration. So lower pH value implies implies higher H plus concentration. So it should have higher H plus concentration. Higher H plus means more acidic in nature. And just like pH is equal to minus log of H plus concentration, we can also define pKa as minus log of K concentration or Ka value, minus log of Ka. So higher the value of Ka, lower the value of pKa. Got it? So here we can say that if the Ka value is more, we can say pK value is less. Suppose considering two acids, considering two acids HA1, and I said its Ka1 value is 10 raised to power of minus 4, and then I have Ha2, Ka2 value is 10 raised to power of minus 8. In that case, if we check out the pKa value here, pK value is equal to minus log of 10 raised to power of minus 4, which is equal to 4. So pK value here will be minus log of 10 raised to power of minus 8, which is equal to 8. So you can see the first one has lower pK value, and lower pK value will always comes with high concentration. So that's what we are trying to check out, that lower pK value implies implies more acidic strength. So here afterwards, we will be judging the acidic nature on the basis of this pK value. The one which has more pK value is less acidic. One which has low pK value, that is more acidic in nature. Okay, beta. I hope all of you understood this point. Okay. First, first factor, you know, on which we will go and discuss the acidic character is from left to right in periodic table. Periodic table. When you go from left to right, you should always check out for electron nuclear difference. So more the electron nuclear difference, more is acidic character. more is acidic character. For example, if you take CH4, NH3, H2O, and HF. Left to right, these are the cases. So from left to right, if you check out, the more acidic character will be for HF. Because here, electronegativity difference is the high criteria. We'll always check out which has more electronegativity difference. HF has the highest electronegativity difference, so that will act more acidic, which means it can give H plus easily. Similar terms, if you go from left to right, if you have SiH4, PH3, H2S, and HCl. Out of these four, HCl will be more acidic in nature. Right? So this is the first case. Second case, in periodic table, as we go from top to bottom, then we have to check HA bond strength. We should always consider HA bond strength. Okay. If HA bond energy is low, acidic character is more. Acidic character is more. So that's why if you check out HF, HCl, HBr, and HI, since you are going down the group, that is top to bottom, down the group, the bond strength keeps decreasing because HI will have least bond because it is bigger in size. So since it has bigger in size, it is easy to break this bond. So therefore, HI is a very, very strong acid here. HI will be the strong acid. Now, if I put the pK values, you remember pK values I told you? Higher the pK values, less will be the acidic character. That is what you will see that when it comes to methane, the pK values are almost 48. This is almost 38. Water is 15.5. Okay, HF is 3. So you can see which is more acidic. Lower the pK value, more will be the acidic strength. While if you check out these bonds, HF, HCl, HBr, and HI, pK value here is 3. HCl is almost -7. This is -9. This is -11. So they are all very, very strong acids. Clear? Not that you have to remember these values. You should know the range. कि किस रेंज में स्ट्रॉन्ग एसिड रहेंगे, किस रेंज में वीक एसिड्स रहेंगे, एंड सो ऑन. Like if you take H2O, H2S, H2SC, and H2TE, if you look at all of this here, as you go down the group, acidic character will increase. So H2T is the more acidic nature. Okay. Next. The third effect is on the basis of percentage S character. So we need to judge on the basis of percentage S character. So more the percentage S character, higher acidic strength. Suppose if we take CH3, CH2H, this carbon and hydrogen bond. Next, CH2, double bond CHH. Thirdly, CH triple bond CH, like this. We have these three. Now we need to check, percentage S character. This carbon, and this carbon. See, this carbon has sp3 hybridized carbon. This is sp2. This is sp hybridized carbon. So percentage S character, if you check out, this is around 25% here, 33% here, and 50% here. So S character is increasing from this left to right. So more the S character, easily you can break the bond here. Easily in a sense, more acidic. Don't think like bond strength is weak. No, this C triple bond H will be more acidic. So if you see acidic character, this is how the acidic character will vary. Okay. In fact, if we check out the pK values here, their respective pK values are around 48 here, 44 here, and 25 here. So you can see lower the pK value, more will be the acidic strength. Okay. Another example in which the same percentage S character comes into account is when you have cyclopropane, cyclobutane, cyclopentane. Now, when you compare this, the percentage S character in these bonds, we have three types of bonds here: this one, and this one. Use this one. Out of these bonds here, this has more S character. Percentage S character is more here. Percentage S character is falling up this way. So acidic character or acidic strength will also vary this way. This will be more greater. Finish everyone. Another case where you will see is that if you have heterocyclic molecule like we have N and H, okay, one more H, positive charge, and then N with H and H, another positive charge. Removing this H plus here, correct, compared to removing this H plus here, if we compare, the acidic strength is this one. This is how the acidic strength will be. Next. This is case 3. Next, check out case 4, where you have inductive effect. Inductive effect, every plus psi effect increases, acidic nature will, or acidic strength will decrease. And minus psi effect, if it increases, acidic strength will always increase. Remember this logic and rest will be questions easily done. Suppose if at all we take HCOOH. In HCOOH, there is no effect. There is no plus psi, there is no minus psi. Next we have CH3COOH. Next we have Me twice CHCOOH. Next we have Me thrice CCOOH. We can see here there is no effect, but here there is one methyl group. So if you check out the plus psi effect, here there is no plus psi effect. There is a small amount of plus psi effect here. Plus psi effect is increasing because there are two methyls. Here plus psi effect is even more, highest. So more the plus psi effect, less is the acidic nature. Therefore, if you check out the acidic character, this is how the acidic character varies. Clear on that? Now, if you check out the pK values for the respective acids here, the pK value of this is around 3.8. Correct? Sorry, this is around 3.18. No, 3.8. This is 4.76. This is 4.86. This is 4.88. Okay. One important logic, easier way to remember when it comes to acidic cases is OFBA. O as in oxalic acid, COOH, COOH. Here, with respect to one COH, the other COH is withdrawing. So we can say that the other one is giving minus effect. Therefore, COOH oxalic acid would be the most acidic. Then comes formic acid, HCOOH. Then comes benzoic acid, PHCOOH. Then comes acetic acid, which is CH3COOH. Okay, so this is formic, benzoic, and this is acetic acid. If you check out the respective pK values here, this is 3.8 and 3.8 was this one. Formic acid 3.8. This is coming out to 1.25. Benzoic acid 4.2 and this is 4.76. So you could guess that which one is going to be more acidic. Clear? Right. Next, inductive cases, if you check out, we used to have CH2, COOH, and some X group present here. Suppose if X group is, hydrogen, or X group is fluorine, X group is chlorine, if this X group is bromine, if this X group is iodine, if this X group is NO2, if this X group is NMe thrice plus, if this X group is cyanide. In such cases, how does the acidic character vary? Okay. So in all of these cases, if you check out the acidic character here, okay, the pK values, check out the pK value here. When it is hydrogen, pK value is 4.76, which is acetic acid. The minute we keep fluorine, it is withdrawing. So acidic character will start increasing. So 2.86, 2.90. For iodine, it is around 3.15. For NO2, it is 1.68. This is 1.86. And this is 2.47. So only exception comes here as NO2 and NMe thrice. Although we usually expect this to have very strong minus effect compared to NO2, this would show slightly better compared to that of NMe thrice. Okay, so this is the acidic character which is to be learned. Not that you have to learn values, you have to learn how the comparison is. That's all. Suppose if you have CH3COOH compared with CH2COOH with one chlorine, next CHCOOH with two chlorines, and CCl with three chlorines, COOH. You can see that how the pK values are. In this case, it is 4.76. This is 2.86, 1.25, and this is 0.65. So which makes it very, very acidic, very strongly acidic. The first one becomes strongly acidic. Next, if you have COOH here, COOH here with chlorine, and COH here with chlorine here, chlorine here. So suppose if you have 1, 2, 3, and 4, if you are to compare the acidic strength. First case, everything is donating. Methyl is a donating group. So the acidic character is pretty less. Second case, chlorine is very near. Third case, chlorine is slightly far. Here it is even far. So the one which is very closest, that will be most acidic. Then comes the third one. Then comes the fourth one. And the least would be for 1. Okay. So this is how you need to judge about the acidic character. Now the same logic can be applied for different dioic acids like CH3, COOH and COOH. COH and COOH. If we check out here, this is oxalic acid we just learned. If that COH is connected via one COOH like this, one methyl group is connected in between. The distance between the COH is increasing, hence their acidic character will decrease. That's why this is how the acidic character will be. So if we check out the pK values, this is around 1.23, this is 2.83, this is 4.19. This is how the acidic character varies. Okay. Suppose in case if we have hybridization issues, CH3, CH2, COOH, and CH2 double bond CH, COOH, and CH triple bond C, COOH. Now, in such cases, you just have to check out which of them is giving what effect. This usually gives plus effect. This is giving minus I effect. This is also giving minus I effect. The minus I effect is most given by the last one, acetylene group. That will be more acidic than the others. So, therefore, acidic character, if you check out, this is how it varies. And if you see the pK values for their respective molecules, it is 4.76 approximately, 4.25, and 1.84. Next, in case of alcohols, suppose if you have CH3OH, on OH group there is one methyl group. Suppose if you have CH3, CH2OH, now there is an ethyl group. Next we have two methyl groups, makes it isopropyl. Now OH group, which makes it tert-butyl, tert-butyl alcohol. So between these four, if we check it out, then CH3OH will be more acidic than this. Because more the plus side effect, these are all more plus side effect, less is the acidic nature. Clear on that, guys? Next, if you compare these groups, we have a group G connected with CH2, COOH. Now this G group could be anything, like starting with NO2, could be cyanide, it could be C double bond OET, like an ester, sorry, OET, an ester, or C double bond O, Me, which is ketone, OMe, and then we have only OH. So out of these, if we check out the order of the reactivity, you'll find that NO2 is the most acidic, next cyanide, next C double bond O, OET, next OMe, next we have C double bond O, Me, we have OH. This is the order of their basicity. Okay. So if you see the respective pK values in all of the cases, I'm just giving you for reference, not that you have to mug up. Okay. So you will see with uh, NO2, we will come across 1.68. This is 2.47. With esters, it is 3.35. With esters, it is 3.35. With this, it is 3.58 and 3.53. Next, 3.83. The only exception here are these two. You can see ketone and ethers.
Are you doing theory or questions, sir? I just joined right now.
You're too late, beta. We are
I'm sorry, sir.
we are finished with the acidic
Theory?
strength. Yeah. Okay.
Okay, sir. So can you check the
Aromatic.
recording of this?
Yeah, yeah, sure. Just check out recording. So these are the respective pK values. Based on that, you can judge what is going to be the acidic character. Now, if you see the phenols, OH, and if you compare that with cyclohexanol, phenol will have relatively very high acidic strength. And the pK values, if you check out, this is around 10 and this is around 18. So we could guess that this is very high acidic nature. If you compare phenol with CH3COOH, then it is checked at as 4.76. This is pK value of 10. So you can guess that. Here, the other day we discussed when you have CH3COH, why this is being more acidic than phenol? Because it would have equivalent canonical structures, equivalent reso structures, equivalent resonating structures of acetate ion CH3CO minus, which is conjugate base. Right. What does this mean? See, whenever we talk about acidic strength, listen up, guys. CH3C double bond O OH. What are we talking here? We are saying that CH3C double bond O minus plus H plus. This is how the splitting happens. More the amount of ionization, more is the acidic character, more is the H plus concentration, more is K value, less is pK value. That's how we are relating here. Now you can see that this is an acetate ion. You can see this is an acetate ion. Now this acetate ion is going to be more stable, with its resonating forms, that is CH3, CO minus and double bond O. So these two are the resonating structures, and these two resonating structures are equivalent resonating structures. Now one thing you got to learn it, whenever an acid is giving a base, got it? It all depends upon what acid. It is a weak acid, then it will give you a strong conjugate base. Acid after releasing H plus will become a base. Base after accepting H plus will become an acid. This logic we must know. Next, if we have CH3NO2, 1 NO2, that is less than acidic nature of CH2 with 2 NO2s, because NO2 is strongly withdrawing, makes this carbon hydrogen bond easily to break. This is how the acidic strength varies. Next, if we have CH3, C double bond O, CH3, acetone, and then we have CH3, CH double bond CH2. Now, if you check out the pK values here, this is 18, right? So this is 43. So you can easily guess that this is very highly acidic compared to that of simple simple alkenes. Now, if you check out CH3, NO2, CH3, CN, CH3, C double bond OH, and CH3, C double bond O, OAT. Now, if you compare the pK values here, right? I mean, sorry, acidic strength here, you would find out that this is more acidic than the others. Clear, dear? Right.